Okay. Yeah, the plan today, I posted a couple of additional, I posted, I think, 2 supplementary material. One is a PDF I'm showing here. The other one is a lecture slides. So I'm hoping to cover those 2 today. So both of them are sort of supplementary to what we covered in this unit. And the first one that I'm going to do is, this is a Poisson one parameter model, and I want to make sure that we get enough practice to make sure that we know how to derive posterior if you're given the particular prior together with the likelihood function. So this is the first one we're going to cover. Then we're going to go to the lecture slides. Just a few pages about multicolor approximation in general. So I want to talk a little bit about the background, and we started using it already in this unit and previous unit, but maybe just a little bit more background and practice and thinking about how we can apply that in various places. And the remaining times we have, I will give the chance for you to work on lab 2, and I'll just walk around and answer questions. Okay. All right. So the first one here, you can take a look here. So this is based on our textbook section 3.2. So maybe some of you read it, so you already know about it. So this is the case that we're still working with one parameter model, that we have a likelihood or the data model from a Poisson distribution. So you probably have heard about Poisson before. We typically use it to model occurrences of events. Okay, and I'm giving you the density function. You write defaults, and then the only parameter. So the unknown variable is y, and then the only parameter is this theta. Okay? And you can see that it has this PMF in this way, and then y, which is a random variable because it's counting occurrences. It goes from 0, and it's always integer. Okay? It goes up to infinity. So we typically use this to model occurrences or events. And then this unknown parameter theta is a rate parameter that we're going to put a prior on, okay, and then make inference about it. Okay, so keep that in mind. We have the likelihood from a Poisson distribution. And the prior that we're going to give is what we call the gamma distribution. So remember, previously we covered using the gamma distribution for the precision parameter. Remember, if we have the one parameter model for the normal that we assume, remember you have y1 through yn from IID, from a normal distribution, mu and sigma. If we assume that mu is known and sigma is unknown, we covered the case of how to make inference about sigma. Okay? And specifically, we assume that sigma squared, or 1 over sigma squared, follows a gamma distribution. Okay? And we showed it before, maybe 2 lectures ago, that the posterior is a gamma, and we show how the derivation process goes. Okay, so gamma distribution is for a random variable which is non-negative, and that's why previously we used for precision, because 1 over sigma squared can never be negative. And here, the rate, which is, you can think about like the rate of some events happening, that's also non-negative. Okay, so we use gamma for that. And the density is like before, we saw it before, so I just write it for you again. And now we come to the derivation exercise. Okay, so I give you here. Now, if I have a Poisson data model and a gamma prior, we're going to put gamma AB, and zoom this a little bit more, gamma AB. And so please write out the prior density. Make sure that you write it in terms of theta, because theta now follows the gamma distribution. Now is also the time for you to practice writing out the complete joint probability density function for the likelihood. So we're assuming that we observe a sequence of y, and each of the y is a Poisson. So try to do that. And then in the end, if you try to derive and recognize the parameters, you will see that the posterior distribution is gamma again. So maybe it's easier for me if I show the Poisson density and then the gamma density on the top. But the task for you is to derive the posterior. Okay, so don't worry about the constants. Just focus on anything about theta And we can spend the next 5 to 10 minutes work it out to make sure that we feel comfortable enough to do derivation for posterior estimation. Okay. That notation, sorry about this. So forget about this, just write exp negative b theta. Okay. Yeah. So I think earlier I should have written e to the power, but don't worry about it. Let's maybe just focus on this one. Okay. Right, so here, yeah, you can work with the proportional sign. I think I just put equation sign there, but really, don't worry about the constants, just focus on, and you will recognize it to be a gamma in the end.
And then I have that
One last comment, right, is whenever you are working with proportional signs, not only that you don't have to worry about the constants from the prior and likelihood, but then in the likelihood and prior, whenever you see something not about theta at all, they all go into the so sometimes you might be confused. I guess in this case, we're gonna have a yi factorial. That's really difficult to deal with, but that's a constant, because that's not about theta. Right, so you can just delete that. We'll go into the proportional. Yeah, so I will start slowly writing it.
But I don't know if that's going to be translated as black. Yes. That's a lot of
Yeah.
So I just took over that. Okay. So, yeah, okay, that's fine.
And the likelihood is a joint their IID, so you have keep writing the constants for now, and later we can delete them. And what we have is following the density function. So keep in mind it's theta to the power of yi. Okay, don't forget those subscripts, because that's part of the data here. So this is for each like contribution of each of the observations. Okay, and it's a product, so we might want to like simplify a little bit more before we go on. So it will be theta raised to the power of sum of yi. Okay? The product, but in the power is going to be sum. And then in the exponent, it will just be n times theta, because you're multiplying n copies of it. And then the division, if we keep the constants for now, it will just be the product from 1 to n, and then all of the factorial here. Okay. So this is, I mean, like I break it into those 2 steps for you, but even for you, like for other situation where you're just trying to derive posterior, it's probably a good practice to write out the prior and the likelihood. Just like put it there so you can grab the terms that you need. So to derive the posterior, like we said, we're going to use the proportion sign, and that means any kind of constant will go away. So I'm going to use a different color to first of all mark what are those constants. So this is a constant from the prior, right? It's not about theta, so I will not need it anymore. If we look at the final form of the likelihood, theta raised to the power of sum of yi, that have to stay, okay? Because it's about theta. The other term, exp, negative n times theta, that has to stay as well. But this term, it doesn't, okay? It's not about theta anymore. So that can go away. So if I go with proportional sign, I will have theta to the power of a minus 1, exponent negative b theta, multiplies with theta to the sum of yi, and then exponent negative n theta. And if I combine this term with this term, and this term with this term, I will have theta to the power of a plus the sum of yi minus 1, and then exponent negative b plus n theta. Okay, so this again, I guess again is simpler than the case that we deal with the normal. You don't have to complete any terms. Well, you do have to combine terms, but you don't have to complete square to recognize the posterior distribution. And we know that this, let me use a different color. This will be the first parameter for the gamma, right? And then this will be the second parameter for the gamma. So that's why you come to this point. Okay. Yeah, so I would say the case where we are dealing with the normal model and then only thinking about the precision, it works pretty similarly. Okay, pretty much you recognize the term, you collect the terms about theta to some power, and then you also collect the terms in the exponential function about negative theta times something. And you combine those, and you should be able to recognize the final form. Okay, so make sure that you're super familiar and like comfortable with this kind of practice, and as well as derivation, because this is a key to all of the derivation goal that we need to do. And in the end, number 4 here and 5, I just want to mention that for number 4, the final result is what we saw. So you start with the gamma AB, you combine with Poisson model, you come to a gamma A plus sum of y and B plus n. Okay, and just quickly remember in the beta case as well as the normal case, we looked at how the posterior mean is a weighted average of the prior mean and the sample mean. So we see that here as well. Okay, so this is the posterior mean. That's just definition from the gamma distribution. It's going to be the first parameter divided by the second parameter. Okay, that's just a known result. I'm going to take that for now. So for the posterior, will just be the first parameter over the second parameter. And then we can break it down into this summation. Oh, let me actually just zoom in. It's probably better to see. Sorry about this. And we break it into this weight times the prior mean, and this weight times the sample mean. Okay. So again, you see how the relationship between the prior mean and the sample mean to the posterior mean. Okay. And what you can see as well is how this effect of n is. Remember, n is the sample size, right? So if you're going to have a large sample and going to be going up, then the second term, the sample mean going to dominate. Okay, and that's another way to see how, like Bayesian inference, when you're dealing with a large sample size, you will be very data-driven in that case. It's less obvious to look at the variance, so we're not going to go that route, but I just wanted to show you that for the 3 different models we covered so far, the beta binomial, the normal, and then now the Gamma-Poisson, you can all see how the posterior is a weighted average of the prior mean and the sample mean. Yeah?
Is that pair set, or can it change? Can we use the beta prior distribution and then use Poisson sampling model, for example? Is that a possible combination?
If you do that, it won't be conjugate.
Oh.
Yeah, so, okay, so that's a great question. So far, the 3 models I was talking about, they're all conjugate models. That you start with a given, like a particular prior distribution, and the posterior is going to come from the same family. Okay, but like what Josh says, well, what if I really want to give a beta prior for some parameter, I guess for the Poisson in this case, and I have a Poisson theta model. If you do that, you can derive it, but the final term, the final posterior distribution, it would not be beta for sure. And it might not be a known distribution at all. Yeah, so you can work with that, but it's just for now, we want to make sure that we can work with conjugate priors, that we know the exact final posterior distribution. So you can either use the exact solution, like those P gamma or Q gamma, that kind of stuff, or a Monte Carlo approximation to any kind of posterior summary. Okay. Mm-hmm. But another thing I should mention is, yes, we started working with conjugate prior because they're nice to work with, but at the end of the day, I think it's more important that you put the prior that you think is more suitable. Okay? So later on, you might go into the situation that, well, I don't want to work with conjugate prior, even though it's nice, because it does not reflect my prior belief. Then you can go any kind of thing you want, as long as it makes sense. Okay, but computation will be a challenge, right? If we don't work with conjugate cases, we don't know exactly what the posterior distribution is going to be. So how are we going to summarize the posterior distribution? pretty soon, next chapter, we're gonna start looking at cases that, well, we won't be able to recognize it, what we can do. And then the technique we're gonna cover is what we call Markov chain Monte Carlo. So Monte Carlo is like, we know what it is, so we sample large numbers of them, and then summarize to use it to approximate. But when you don't know what the posterior distribution is, then we're gonna use what I call Markov chain Monte Carlo, and that can help you to get a good approximation to the posterior distribution. Okay, so we're gonna see that from next week. But to address Josh's question, you can go any prior if you want. And so far we cover conjugate prior just because it's easier to work with them. And we get enough practice, hopefully, to do all of the derivation exercise. Anything else? Okay. All right. So this is the part about the exercise. I will update. I think that has some typo here. So I'll update the document and upload it again. And the other topic. Oh, stop talking.